Hello everyone, welcome to DP Tutorials by Donny Jarwa. In this teaching lesson, we will learn and focus on one implication, which is the application of a potentiometer, where we will try to compare the EMF of two cells. Now, we have already learned that a potentiometer is nothing but a device in which a steady current flows through. So this is our potentiometer, and in this potentiometer we have a set of wires which are connected on this wooden boards, approximately 5, okay, approximately 5 to 10 wires we usually use to connect. Usually 5 up to 10 wires, okay, depending upon the construction from the lab, okay, from the manufacturer, I mean. Then over here in this particular derivation or experimental setup, we will try to compare the EMF of two cells. In this case, we have these two cells, and both these cells will be having different EMF. The cells taken in the lab might be pencil jockey, or it might be Laclanchi cell. Okay, it might be Laclanchi cell, okay, Laclanchi cell or Daniel cells, okay, Laclanchi cell or Daniel cells, in which we will try to compare the EMF of both these cells. Okay, we will try to compare the EMF of both these cells. Now, over here, also we have, let us reiterate that when we are using an experiment, or when we want to find the potential difference, or when we are measuring the EMF of the cell by using a potentiometer, we have to supply constant current, or steady current should be maintained across a potentiometer. So from here, always remember that a steady current should always be maintained across a potentiometer. How will we maintain constant current across a potentiometer? Like in this case, a potentiometer will consist of these wires: the first wire, the second wire, the third wire, the fourth wire, and the fifth wire. Now we can obtain this steady current in a potentiometer wire by by adjusting the amount of current by the help of this rheostat. Now a rheostat is nothing but a device which regulates the amount of current in an electric circuit. Now we have this battery. It's a battery which is the potential source, where we have connected to the first terminal of the potentiometer wire. Say, like for instance, if this might be that point P, and this terminal, okay, let me consider that this is that first terminal, which is the point P, and this is that other terminal, which is the point Q. So this will be the first wire, and this one over here corresponding to point Q, that will be what? That will be the last wire. Okay, so from here, let this battery be connected across these two terminals of the potentiometer wire, and this battery will be having a certain potential. Suppose let the potential of that battery be what? Be denoted by V, and we have this key here. Okay, we have this key here. Let this be the 1V key, and by inserting the plug from the 1V key, current will flow on the circuit. Now we already know that this is the positive potential of the battery, and this is the negative potential of the battery. So this will be the negative terminal of the ammeter, and this will be the positive terminal of the ammeter. The ammeter is nothing but that device which helps us to measure the amount of current flowing in an electric circuit. Now over here, then when we insert the key, okay, when we insert the plug from this key, then obviously current will flow on this circuit. Okay, current will flow on this circuit, and will flow in this direction, and then you will find out that the current will be, there will be some deflection on the galvanometer. Now we can adjust the current which flows through this potentiometer by the help of this rheostat. See, typically in the lab we will adjust in the range of this ammeter will be in the range of milliamperes. So let's suppose if we fix this current at 150 amps. So with the help of this pencil jockey, with the help of that pencil jockey, if you touch the pencil jockey and the first wire, if you touch the pencil jockey the first wire, or if you touch the pencil jockey and the fourth wire, that current will always read at 50 milliamperes, which means steady current should be always be maintained on the potentiometer wire. Now, having said that, then we will try to compare the EMF between these two cells. These two cells. Now over here at this terminal P, we will connect this fast EMF, this first cell. Suppose let the EMF of this cell be E1, and again with respect to this cell again, with respect to that terminal at point P again, we will connect another cell. We will connect another cell which is having what? An EMF. We will connect another cell which is having whose EMF is what? Whose EMF is E2. So this will be what? The schematic diagram. Now across, if we want to find the EMF across these voltages from here, if you want to see if this will be the positive terminal of the cell and this will be the negative terminal of the cell. This will be the positive terminal of the cell and this will be what? The negative terminal of the cell. So current from here will flow on this direction. Current from here will flow along this direction. Even from here also will flow on that direction. Now from here across the cell we will use this three-way key, but in this case this figure is a four-way key. That means by connecting from these terminals or these points we can find the EMF. So over here this is nothing but a commutator. We call this as a commutator, or a four-way key. We call this as a commutator. This is a commutator, or we can describe it as a four-way key or a three-way key. In this case we require a three-way key having plugs. We can take out these plugs and there will be gaps. So over here let this be the point, the terminal A. That will be the point where we will insert. This will be A. This will be that socket B, and let this be C. So from here, that means over here we will connect along this point, along the second cell we'll connect across the point C, and from the across point B, and from this plug besides the third plug, we will connect across the galvanometer. From the galvanometer we'll connect across the resistance box, and from the resistance box we will connect across the one-way key. See, like for instance, in this case when we are doing this particular experiment, or when we are doing this particular analysis or activity, we will have to insert the plug when the key, suppose when the key K is inserted, when the key K is inserted between A and B, when you insert the plug, when you take these plugs, when you take those plugs, and then when you take these plugs and insert it between these points A and B, or between these points A and C, when you insert the plug at this point, and when you insert the plug at this point, then current will flow. Let me mark it very suppose when you insert the plug at this point, when you insert the plug at that point, and when you insert the plug at that point, then what will happen? Current will flow from the first cell. So when current flows from the first cell, that means what happens? What happens on the wire? What happens on the circuit? That means over here current will flow in that direction. Current will flow on that direction, and you will find a null point. See, like for instance over here we will obtain the suppose the null point. Suppose the null point is obtained somewhere at that point. So this will be that particular point. Suppose let me mark this as J1, the jockey, by sliding the jockey J1 at this particular point, we will obtain what? We will obtain a zero deflection on the galvanometer. So over here we have that means on a galvanometer, this will be your galvanometer. This galvanometer will be on this form, and over here we will have the 30 division, 0 division, the 30 division, and also what, the 30 division. This is your galvanometer, and we will have the needle, and we will have, well, by sliding this jockey on this wire, that means this needle should point what, should point at 0 deflection. We have to find that point within the meter bridge wire by sliding this jockey such that it gives us what, it gives us 0 deflection on the galvanometer. That 0 deflection on the galvanometer is known as, is described as the null point, and the length corresponding to the null point is what is known as the balance length. Okay? Balance length. So from here we have insert. Okay, I have written over here that when the key is inserted between the terminals E and B, E and C, I mean between these E and C of a three-way key, then what will happen? The current of a three-way key, then the current will flow in the circuit of from the first cell. So this is our first cell having EMF E1. Okay? Whose EMF is what? Whose EMF is E1. Then the null point is obtained at this particular point and corresponding to this length. So this is your first wire. Okay? This is your second wire. Say preferably the length will be around 150 centimeters. So that length will be denoted by what? Will be denoted by L1. So we already know that when we are using the potentiometer wire, the potential drop, this is the working principle. The potential drop is directly proportional to what? To the length of the to the balance length or the length of the potentiometer wire. So as the potential drop across the potentiometer wire is directly proportional to the length, then we can write, okay, we can write in this way. So with respect to this E1, okay, with respect to that E1, we can write E1 is directly proportional to L1, which implies that this E1, the cell E1, is equal to 1, is equal to K L1. So we can mark this as 1. We can mark this as equation number 1. We can mark that as equation number 1. So this is the first step. The first step is by inserting the plugs between these 2 points A and C. Okay, between these 2 points A and C. So from here, what happens? Suppose if I insert the plug between point B and point C. When you insert the plug between point B and point C, then current will flow across the second cell. Okay, the current will flow across the second cell. See, in this case, I will remove this plug, okay, from there, and then I will insert between points between points B and C. When you insert the plug between point B and point C, say if you insert over here, insert the plug over there, and if you insert the plug over there, then what will happen? The current will flow along the cell E2, okay, along the cell E2. So when the current flows along the cell E2, so from here, that means in this case, okay, in that case, the current will flow along the cell E2, and when this current flow, it will flow on that direction. Then when you the current will flow on this direction, and then suppose by using this jockey, that means the jockey, the null point somewhere you will obtain over here. Suppose that will be the null point corresponding to the second cell. Okay, null point at this particular point within the bridge wire, you will obtain the null point. So let that be J2. Okay, so by inserting the plugs between B and C, when the key is inserted between the terminals B and C of this commutator, okay, then the current will flow in the circuit from what? From the second cell. So when the current flows from the second cell, then this second cell will be having EMF E2, then there will be null point corresponding to this, and then that null point also will correspond to what? Will correspond to the balance length, and let L2 be the balance length corresponding to the null point from the second cell, okay, having EMF E2. So in this case also we can write this relation that E2, okay, that E2 is directly proportional to 1. The EMF from the second cell is directly proportional to the length, to the balance length, or to the balance length L2. Okay. So from here, that means, which means that E2 is equal to K L2. Okay. So this will be what? This will be equation number 2. So what is this K? Okay, this K is nothing but the potential drop. Okay? This K, not potential drop, sorry. This K is nothing but our potential gradient. The potential gradient for potentiometer is always constant, okay? Irrespective of the cells, okay? Irrespective of the cells. So in this case, if we want to compare, when we are comparing the EMF of different cells, that means we have to divide the two equations. Okay? When we are doing the comparison, that means we have to divide equation 1 by equation 2. So comparing the EMF, that means mathematically we are dividing equation 1 and equation 2. So from here, when we divide equation 1 and equation 2, which means that left hand side of 1 divided by left hand side of 2, and from here this will be equal to 1. This will be equal to K L1 divided by K L2. So from here we can got, that means by knowing the values of L1 and L2, knowing the values of L1 and L2, we can compare the ratio between the EMFs. Say like for instance, okay, which means that is over here, okay, that is E1 divided by E2. This will be 1. This will be equal to L1 divided by L2. Okay, L1 divided by L2. So from here, this is that result. Okay, and in the exams, this derivation till this particular step will be around preferably 2 marks. And suppose let us solve an example. Okay, if you want to find the comparison of EMF between these two cells, say like for instance we get L1 to be supposed equal to 100 centimeters and the balance length corresponding to the second cell, say it might be 150 centimeters. Now if we compare the EMF of these two cells, that means E1 divided by E2, we will not know. Okay? EMF of first cell is question mark, the EMF of the first cell is unknown, and even the EMF of the second cell is unknown, but we can compare their EMFs. Okay, suppose from here this will be 100, okay, L1 divided by L2. Okay, so when we cancel over here, we'll get around 2 divided by 1. Okay, 5 2s are 10, 5 3s are 15. So we'll get the ratio of 2 by 3. Okay, we will get the ratio of 2 by 3. So over here, which means that this will be what? This will be that typical example where we want to find DMFs. Okay, DMF. And keep in mind that what is EMF? EMF is nothing but the potential difference of the cell in an open circuit, and terminal potential difference of the cell is the potential of the cell which is in a closed circuit. Let us just recall. Okay, let us recall the relationship between EMF and voltage. Voltage is also known as what? Terminal potential difference. Okay, voltage is known as the terminal potential difference. Now, in an EMF, okay, in an EMF, which is nothing but the electromotive force, it is nothing but, that means when we have a battery, that means we are supplying charges. Okay, we are supplying charges, and when we supply charges, that means we are doing some kind of an energy, electrical energy. Okay, we are doing some kind of what? We are doing some kind of an electrical energy. And when we do electrical energy, that means we are forcing a unit charge, okay, unit positive charge to move from the positive end of the cell to the negative end of the cell. Okay, from the positive end to the cell or the negative end of the cell, round a closed circuit. So this is a closed circuit. So now it is nothing but the work done per unit charge. Work done per unit charge is nothing but what? Voltage. So the work done in driving a unit positive charge, see if I have the plus charge plus Q, in driving a unit positive charge once around the closed circuit, that is defined as the EMF of the cell. But what is potential difference? Okay, what is terminal potential difference of voltage? This is nothing but the amount of work done per unit charge between 2 points. Okay, 2 points of an electric circuit, 2 points of an electric circuit. So 2 points, the work done in moving the charge between 2 points in an electric circuit. See, I can even find the voltage. Okay, I can even find the voltage between these 2 points P and these 2 points Q by connecting, by using what? By using a voltmeter. Okay, even at this particular point, how will you find the potential at this point A and point B of this resistance wire? You can find that potential by using what? By connecting a voltmeter in parallel to this resistance wire. So voltage or terminal potential difference in an electric circuit, it is in between what? It is between two distinct points. Okay, two distinct points or between 2 points in an electric circuit. It is equal to what? It is equal to the work done per unit charge. Okay, work done per unit charge. Work done per unit charge is nothing but voltage. That is why voltage is one. Voltage is joules per coulomb. Then against a static electric field to move a test charge to these 2 points. So from here, if this is the positive potential and if this is the negative potential of the battery, so you're moving, you're driving from, that means if this is positive potential, that means this end of the wire will be at a positive potential, this end A of the wire will be at a negative potential. So you are moving from a high potential region to a low potential region. So when you are driving the charge from a high potential region to a low potential region, there will be what? There will be loss of energy. There will be loss of energy. So if there is loss of energy, that means it will be compensated or manifested in the form of work done. So these are some of the key features. Okay, EMF for the cell is nothing but the amount of work done in driving the charge around a closed circuit, once around a closed circuit. The terminal potential difference is nothing but the potential difference of the cell between 2 points within an electric circuit. So over here, also keep in mind that we can find the voltage in a closed circuit and the EMF will be in an open circuit. Current flows, okay, current flows in a circuit, there will be current flow in a closed circuit, current will flow. There will be current flow in a closed circuit, there will be no current flow on a open circuit. So these are some of the key ideas that we need to remember, the differences between EMF and voltage. So just go through these discussions which we have learned, because these are important things or things which are very pertinent from examination point of view and also for catering to your day-to-day concepts. Yeah. Until we meet again, thank you.